All right, let's knock a few of these things out. Let's do another collision problem. This is one box hitting another box. The initial box is going at 2 meters per second. The other one is still. And this guy is going to hit that guy. And then I'm going to look at two different situations. One, an elastic collision, which means that all of the energy is conserved. In that case, what's going to happen is, well, basically what's going to happen, because these two boxes are the same, this guy's going to start going and this guy's going to stop. We're going to find that out. But the other thing we're going to do is we're going to see the other limiting case where all of the energy, or the maximum amount of energy, is lost, which is this totally inelastic collision. And that has another situation associated with it. So both of these, because they're collisions, conserve momentum. But they both have different secondary conditions, not collisions. This one, it's elastic, that means it conserves momentum, or conserves energy. Excuse me, it's a collision, so it has to conserve momentum. And this one's totally inelastic, which means that the final speeds are equal. Actually, the final velocities are equal. They have to be going in the same direction. So that's what we're going to look at. We're going to start with this one here. So we've got the two situations. We conserve our momentum. And over here we're going to conserve some energy. And conservation, for physicists, remember, just means that before and after a situation, the total amount for the system happens. So before and after the interaction. So in this case, the interaction is this box hitting that other box. It could be any sort of interaction. So it could be an electromagnetic interaction. That's the normal one. I'm trying to think of another good one, but I can't. Not right now. Okay, so I'm not going to think of another good one. So usually it's contact, or it's going to be electromagnetic. It could be with more fundamental forces. You could do this with gravity if you were talking about two meteors coming close to each other but not hitting. They would also act like a collision. So that's interesting to note, but it's not something we have to deal with in this class because it's complicated. So conservation momentum means that the momentum, which is the mass times the speed, or velocity really, but we're just doing things in one dimension, so we don't have to worry too much about the difference, except that this number could be negative. All right, so m times v is equal to, right, the mass times the mass of this guy times his initial speed, this guy, is equal to the mass of this guy times his initial speed, 0, which is why nothing appears there. And afterwards, we don't have any limits on what their speeds can be. So instead what we have is some limit on what the energy over here is, right? So we have two possible velocities over here. U, which is the velocity of the guy that was initially moving, and the capital U over here, which is this guy over here that was initially stationary. So then we move on from that, and we look at the conservation of energy, which is 1/2 mv squared. Now this is all just kinetic energy. 1/2 m little u squared plus 1/2 m big U squared. Okay, so we have both of these conditions here. First thing you notice is that the momentum has mass in each thing. So really you have a relationship between the speeds because these two masses are equal. The initial speed is equal to the sum of the final speeds. And here we have a common factor of m over 2, or m times 1/2. So we can cancel all that out. And so now we have v squared equals u squared plus big U squared. And this lets us do a little bit of logical reasoning. Right, so we can square this, and it may have been a little while since you've done this, right? But if you square this guy, you get v squared. If you square this guy, you get u times u, which is u squared, plus big U times big U, which is big U squared, plus U times big U, which is U, plus big U times little u, which is also UU, so you have two of those guys. Now this is going to be easy because now we look at these two situations and we know v squared is equal to u squared plus u squared. And that means that we can just substitute this v squared in here. So v squared is equal to v squared plus 2uu. And you can cancel out those guys because they're equal. So that means that u times u is equal to 0. That only happens if u equals 0 or big U equals 0. Okay, so that's the only way to do that. One or the other or both. But it can't be both because the sum of little u and big U has to be greater than, or has to be exactly equal to, excuse me, this v, this initial speed, 2 meters per second, right? So little u plus big U is equal to 2 meters per second, and one of these is equal to 0. So how do we figure out which one is equal to 0? Well, we look at this and we say, okay, if this box hits that box, that's what we are assuming, then if this one keeps moving, it had to go all the way through this other box. Now, we may not have discussed this before, but you may have some intuition about this, right? It turns out that one thing can't pass through another thing, so that's maybe a third condition, which you might call common sense. You can't take a box, hit it, and it'll go through the other box. If you did have a box like that, then what would happen is you have to break this other box, and then it would not be an elastic collision. And probably a lot more interesting things would be happening. So that means that this guy has to stop, all right? Which means that little u is equal to 0, which means that big U is equal to 2 meters per second. And we actually wanted to find both of the speeds, so little u is equal to 0 meters per second. So that was a little bit of logical reasoning in there, but it's sort of enough for us. So I guess I did that so that I would have extra room, but I didn't need it. Hopefully I won't need it for the next part. So that's what happens with the elastic collision, in fact, is that you get this complete transfer of momentum because these guys have the same mass. You get a complete transfer of momentum. Actually, is that always true? Actually, that's always true. So you'll always have a complete transfer of momentum when you have two objects with the same mass that hit each other. So that if you have this box going at 2 meters per second and this guy going at 1 meter per second, after they hit, they'll switch speeds, right? So that this guy will slow down to 1 meter per second, and this guy will go down to, or go up to 2 meters per second for an elastic collision. Only for an elastic collision. That's not true for an inelastic collision. If there's any energy loss, this is no longer true. But this conserves energy and it conserves momentum. In the case, of course, where these two masses are equal. How about totally inelastic? In that case, we still conserve momentum, but when we write this out, we have our mass times our velocity is equal to the mass times the velocity of one of these guys plus the mass times the velocity of the other. And the second condition after conservation of momentum for a totally inelastic collision, the condition that's associated with the maximal energy loss, is that these two numbers are the same. Basically, the two objects stick together. I don't know why the two boxes stuck together. It could be for any reason whatsoever, right? You could put Velcro on one side or the other. It could be because, they're not really well made boxes and there's some, spurs out there and they lock. It could be because, somebody stuck their gum on one of them. It doesn't matter the reason. Whatever the reason, if these two boxes stick together, then you have a totally inelastic collision, and they lose the most amount of energy that they can in the collision. Any other possible collision will retain more energy in the motion. All right, so now we just say that, well, that's equal to 2 mu. Can cancel out the big m's, which means that u is equal to v over 2. The two boxes going together are equal to have the speed that's equal to half the original speed, which is 1 meter per second. And that's my answer, which makes a little bit of sense. If you have one thing going at 2 meters per second, and then it doubles its mass, then it's going to have to reduce its velocity by half. It's not so scary, right? So that's basically the two special kinds of collisions. So every collision, whether it's a special kind or not, is conservation of momentum. Every single collision that we know of. And actually, that's a fundamental law of nature. The conservation of momentum is a lot more fundamental than it sounds. And so that is true of everything, not just these two special ones, which is your elastic here. These are the limiting cases. Elastic, you keep all your energy in your system. And inelastic, you have the final speeds being equal because you lose as much energy as possible. And of course, you can show that if you want to use calculus. I don't know if you want to use calculus, but you can show that if you want to use calculus. There might be an algebraic proof, but I don't know it. And last time we looked at some other kinds of collisions. We looked at just conservation of momentum, which meant that we specified not only, one of the initial speeds. Not only do we actually both of the initial speeds, we took one of these final speeds and specified that as well. That's another way to do this kind of problem. It's another way to write such a problem, right? And so that gets you basically all three of them. So if you'd like, you can do the same thing for all three of these, right? And you can look at what happens. So you can say, okay, I don't really believe you, right? I don't really believe you. I don't think that if conservation of momentum is in place and you have a collision, that this situation where they're both moving after the collision has the least energy. And you can look at the different possibilities, right? Obviously, this has the most, I just said. Remember, you have to always have the conservation of momentum being true. So you can pick some other numbers that also conserve momentum, maybe 1.5 meters per second and 0.5 meter per second, right? And you can calculate the energy, and you'll always find out that it's between the energy that you calculate here and the energy that you'd calculate here. Okay, well, I think that's probably enough for this problem. I hope you're having a great time, and obviously I'm having a great time, because what could be better than this? So I will talk to you soon. Bye now.